So let's continue with our afternoon session, and it's my great pleasure to introduce the next speaker, Professor Maxim Kontsevich from IHES conference. And today he will talk about fractal dimensions of critical loci.
Okay, thank you very much. And thank you for the presentation. First conference. So we'll speak about some kind of very basic notion of dimension. Let me start with natural numbers. And natural numbers are like 0, 1, 2, 3. And these natural numbers actually represent many things. First, it's represent cardinalities of finite sets. So this is order of combinatorics. You go some identity between numbers, so you try to identification of finite sets. So natural numbers, isomorphism classes for finite sets, but also if you develop a bit more advanced mathematics, there's a sizes of vectors. How many entries in the vector, or what is the dimension of vector, finite dimension vector space? It's again 0, 1, 2, 3. But this is linear algebra and non-linear version of vector space is a manifold. Manifold is something which locally looks like a vector space, and it also has dimension, which is again 0, 1, 2, and so on. Yeah, so. So we're completely used to this natural number. So for us, it's kind of what given 6, 0, 1, 2, and so on. And I want to explain to you there are some numbers in between which also to consider as God given. The simplest one, the smallest one was number is not up to 0, it's not 1, it's 1 over 3. Yeah. Oh, sorry. Yeah, so this dimension is this kind of basic innate attribute of a non-empty manifold. Yeah, so each manifold, maybe it has different cut pieces, but this has a piece of largest dimension. And the manifold vertically is non-empty. For example, if you are a three-dimensional manifold and identify yourself with one-dimensional manifold, that means you are empty. Yeah, so so this dimension you can define in great variety of ways. So that's why it's so fundamental. Whatever you want to call dimension, you write with the same number. And what is the dimension of manifold? The first definition is not actually from these printers. Number, it's kind of not really formal definitions, like 18th century definition, number of independent functions. What is independent? Yeah, or you can send it maximal number k so that you can subjectively map the guide to some, let's say, closed ball. Sorry? Sorry? Oh, but it's kind of ugly functions. I think it's like 19th century. Smooth maps, yeah. Not continuous maps, yeah. But yeah. Or you can try to map your manifold onto the ball, or you batch the ball into your manifold which gives the same number. Or you can just relate to remember that manifolds are something which locally look like vector space. So you choose generic point, you take tangent space, approximate your space by vector space, and see what is the dimension of the space. Or you can cover by goes with some kind of metric geometry. You use a metric. Like if your thing is embedded in some high dimensional vector space, you make it use metrics, and you start to cover by epsilon balls. The epsilon is very small, and the number should grow polynomial and exponential with dimension. Or you can make disjoint balls, so cover your disjoint six, you get the same growth. Or there is something what we call calculable dimension, start to cover balls with various radii and sufficiently small to take the sum of powers, and then see it's convergent to something. This also has Lebesgue coverage dimension, So for each covering, you can make refinements at most, let's say, 3 open sets of sets like this. Or you can do it depends some homology. You consider something called like dualizing shift, or more practical terms, you remove point from a manifold and see homological pair, and homological pair will be concentrated in degree, which is this dimension. Yeah, actually, when we calculate dimensions, there are kind of various activities you do with your complex manifolds. Then you consider the complex dimension, which is half of the real dimension, so it's really beautiful convention. What is actual dimension? And also in complex geometry, you can calculate homologically what is dimension, like what is maximal index of non-trivial x group between 2 coherent sheets. And it's all related to modality. Yeah, so there are plenty of ways, but you see always the same number. So what is the goal of my talk? I just want to introduce for many objects, systematic objects, some kind of fractal dimension. Sometimes it's integer, sometimes it's fractional number. And then for the same object, sometimes you can see different approaches to get the same number. Yeah, so this kind of main running example for me will be critical locus of a holomorphic function. Singularity. It could be, at some point I'll mention that one can do something for not only complex version, real world as well, for real function. So some strange rational number, or eventually one can see that one can define some fractal dimension for things which people like in algebraic geometry non-reduced variety. Then you get a scheme with importance, something like fact point. Also create certain dimension for this. Or you can go to Hodge theory, through variation of spiritual structures on C star. Or one can define things for differential equations on a formal disk with meromorphic connection and regular singularity. And there are 2 versions how we can extract number which would call dimension from pure algebraic situation, which is not manifold, no distances. You get some triangulated category, infinity category. And there are 2 different versions. It could be either Z2 graded and Calabi-Yau category, or Z graded without Calabi-Yau property. Still we can define some number. Or finally in physics, this notion of superconformal theory, which in 2 dimensions, which produce categories and some kind of stuff, some directed objects, and the main number of to conformal theory central charge. And it was meant to be kind of like dimension of the target. And in simplest examples, it's you see non-integer number. Like for Isaac model, you get some charge on half. Also, it's closely related. Yeah, so there are different contexts, and you will see different dimensions. And why I'm talking this, it seems to be absolutely fundamental notion, and one should have, like for dimension, usual dimension, we have many ways to understand things. It's really will be great thing to understand this number from different viewpoints. And this, so the whole story comes from kind of like workshop of some discussions with Diniaru, who spent sabbatical at HES, and Danilo Katsakov, who didn't spend sabbatical, but spent half of time at HES and all. Yeah, and so our discussion was the role of this dimension. It's some kind of like notion of size of dimension. You can fit kind of elephant in your pocket. Yeah, so that's basic. That's kind of basic ideas. But and with a potential application for rational equations, and if one believes appropriate conjectures, it gives a very strong abstraction to rationality. We grow between the variance, and so this topic will be discussed in several talks in 2 days. It will be multiple mirror symmetry conference. starting day after tomorrow, and I will give the talks, and also there will be several talks about this topic. Not about dimensions specifically, but about the whole idea application to fractionality. Yeah, so what's the basic example where we kind of completely show what was going on? It's called quasi-homogeneous isolated singularities. You can see the polynomial. Oh, sorry, so many space. We have a quasi-homogeneous polynomial in several variables. What does mean quasi-homogeneous? If you assert to each variable certain weight, rational number, the weight of each monomial will be 1. So this is small numbers wi for each coordinate, and the dimension associated to this object polynomial will be sum 1 minus 2 wi for all variables. Now, so what are basic examples? You have first you have more singularity, sum of squares. Then definitely the weight of each variable is 1/2, twice 1, and then contribution for each variable will be 0, so then the dimension is 0. So the more singularity gives isolated point without any multiplicities, and this point has dimension 0, it's fixed. But now consider modifying it into a function, like for example, replace the first monomial by cube. So the first variable will have weight 1/3, and its contribution will be 1 minus 2/3 and 1/3. I mentioned 1/3. This is 1/3 which I will mention from the very beginning. It's kind of minimum possible dimension. And you can do something for, let's say, AD singularities based on in diagrams. For example, AD singularities is fifth power, third power, and x squares. And then the dimension will be 14 over 15. So it's another of these numbers, which has multiple interpretation. Why is the right answer? These numbers are sort of quasi-homogeneous singularities, and that appears kind of twice. Originally, first in mathematics, it was Arnold and Marshall later. They introduced something called complex singularity index. They also thought it's kind of like complexity of number of singularity, but they introduced the wrong factor. They have what are called half of dimension. Yeah, so it's a cube they call it 1/6, 1/7, 1/3. So they make mistake twice. And also the same again after normalization quantity appears in physics as a central charge, but now it's overthought. Physicists make it 3 times bigger than it should be, and it's central charge of superconformal theory and also the superpotential. And in early days of conformal theory, people realized that there is kind of parallel between isolated singularities studied mathematicians and this conformal theories and catastrophes with isolated singularities. Yeah, in fact, this complex singularity index defined mathematicians. It works also not only for quasi-homogeneous singularities, but for any isolated singularity. And the physical interpretation is less clear, maybe limited central charge. It was clearly not conformal theory. So why don't integrals are important? These are exactly all singularities when this dimension properly normalizes less than 1, strictly less than 1.
Okay.
Third?
And that's square.
I think that's fair, but this stabilization doesn't play any role. Yeah, so the more singularity is the only singularity which has dimension 0, or all other singularities is dimension is positive. Yeah, so it's kind of psychologically the most important thing is to call it dimension. Yeah, for example, I talked to Watchenko last summer. He was essentially one who introduced these things, and he never understood that this is dimension. He thought it's not like complexity. That's why it makes you kind of mistake by normalization twice. Yeah. Yeah, and the dimension is always smaller than the dimension of embedded space. So it's something between 0 and dimension, and it's a very random stabilization. You get various squares, and it doesn't change yet. Yeah, again, in the simplest case of AK singularities, the function is zk plus 1. Then the dimension, is 1 minus 2 of k plus 1. And when k became larger and larger, it became bigger and bigger, but never became close to 1, which is this one-dimensional object. It sits in C. It's fat point in C. And so the image you can have in mind that you have thicker and thicker point, and will approach more and more form power series, which will be will have dimension 1, but depending on level of notation, will be smaller than 1. Okay. So sorry?
To go back to the language of the less than 1 is a very important.
Yeah, kind of, yeah, kind of. Yeah, also some relations here. Yeah, so what would be the definition of this number? I have different theories. Yeah, first of all, I want the main story, I want to find some not isolated singularities. And the general setup is not very totally general, but it's sufficient for the talk. It's supposed to have a complex manifold, not necessarily algebraic, and we get a holomorphic function. So the critical locus is compact. And this invariant, it's invariant on critical locus. You can replace your manifold by arbitrary small neighborhood. Non-critical points are kind of irrelevant. And also, I think it's not empty. Yeah, if it's empty, as I said, you can declare yourself a manifold of any dimension. Yeah. And also, because it's kind of, you have different critical components of critical locus, you can shift function and so that stabilize one, say, component of cell and components of critical values is equal to 0. And here's the main conjecture which I want to make about this, that suppose you have this non-empty critical locus with critical value 0, and consider any smooth non-negative density, the infinity density with complex support, which is strictly positive on critical locus. You look at smooth and extend by 0 far away. And then take direct image. You get a density on C. And the conjecture is this density is not smooth. What does it mean that density on C or R2 is not smooth? Its density will be definitely with complex support, because you consider complex support, right? Not smooth means that if you make Fourier transform, it doesn't decay faster than any power. So it should decay as some power. Yeah, so it's kind of a bit convoluted way to say things. So we say that there is some number which in fact I expect the rational, which will be this dimension. It does depend on just the density. So that if you make Fourier transform with a direct image, or the same as you calculate this integral exponent of I times this linear form of your function f, epsilon small complex parameter equals to 0, then it seeks decay as a power. And the coefficient of the decay should be strictly positive number, so it's not 0, and exponent will be something which we call complex codimension of the singularity. Okay, yeah, that's yeah. I don't really have. I will go to one can try to calculate it that, but it's definition. If it's true, then that will be the definition of the dimension. No. Yeah. So the situation is the following. Function has more singularity, you can easily calculate the since the dimension 0, so exactly as I promised to you. And if it's more singularity, so it's some squares, some variables and constant belong. First k variables, so the critical locus will be submanifold, the function will be Morse in transport direction. Then the dimension will be dimension of this critical locus to the dimension of subarray k. And in finally, we got this function z to power k, then we get 1 minus 2 k. This example. Yeah, so this fits completely with this examples which we know, but now for non-isolated singularities. Yeah, I just want to say that this conjecture about direct image is wrong if you replace your variety by complete by real variety. It's very easy to hook up example of variety with a function and non-trivial critical locus such that direct image is smooth. You take, for example, two planes and you take a function which is sum plus sum of squares minus sum of squares another, and take densities concentrated near zero. Then the direct image will be like Lebesgue measure on positive numbers, Lebesgue measure on negative numbers. You add together, you get Lebesgue measure of smooth everywhere. Yeah, so the 6 can cancel, and also periodic numbers that can cancel. But it's can really well affect some very false instances. Yeah, so it's conjectures out of which at the moment, and I think it's deep. It's not, it will be not easy to prove. And then we make a definition that number delta is this each number is a dimension of singularity, each number represents the exponent. Yeah, what will be n minus delta. So that's this definition. Yeah, so what here goes on? I said the definition style of our it's not what they were doing in the period when you consider this complex singularity index for isolated singularities. They consider integrals of exponent of your function, but not of a whole complex manifold, but over real sites. They don't put real things. You get kind of multivariate function and consider again linear order of singularity. And this seems like kind of like Hermitian square, and it's closer related, but presumably for isolated singularity is the same number. The constant term which appears as the gross which is a positive number. It's a really bizarre guy. Yeah, I just checked the most stupid example. I take homogeneous polynomial defined with smooth coupled surfaces in projective space. And what is this number? If the degree of this polynomial is very big, bigger than the number of variables, then we'll calculate some conversion critical 6 positive number. But if it's like cubic polynomial in 10 variables, you write kind of name integral your function power of minus 10 over 3. It's divergent integral. You should kind of regularize it, go to some Cauchy theory, and then eventually check to get non-zero numbers. It's actually square of norm of some realization, some pure Calabi-Yau models. Yeah, so these numbers already for continuous 6 gives the Calabi models, independent of what degree for the degree how number variables you get hidden Calabi-Yau something here. And specificity is the heart of the vector, so it means that you can really cancel things for several singularities. The positive numbers they only accumulate, you can never ever cancel. And this is the essence of my conjecture. And yes, should go through polarization for zero, but it's still not clear to me. And this dimension is, if you look at the definition, it's clearly behaves additively when we make like Tom-Sebastiani sum. You just take product of varieties, take some pullbacks of functions, then you take product of integrals, the process. Obviously, idea. Yeah. So what reminds me? It reminds me something from metric geometry. Suppose have a complex subset of Rn. For example, on your screen you get just put many dots basically for Cantor set or whatever. It could be Cantor set or Sierpinski Gatsky, some kind of really ugly fractal stuff. How to define this? It's Minkowski dimensions. It's not exactly Hausdorff dimensions. it's for subsets of Euclidean space. Yeah, first of all, if you pick some number delta in R, I define what is the delta volume of this subset. Namely, I take epsilon neighborhood of my subset, I get open subset, because open it has some well-defined Barré measure, this volume. I take volume, now multiply by appropriate power of epsilon, yeah, take a limit. Also, lim sub when epsilon goes to 0. I get definitely some number, could be 0, infinity, or some finite number. Okay, now we get this volume depending on delta, and now if you look how this volume depends on delta, it's behaves in a very stupid way. Up to some point it's infinity, and then after this point it's 0. So there will be some there's only one value that it kind of jumps. It still could be volume could be 0 infinity. This is that point. It will be in a costly dimension. Yeah, so if you do not have fractal set but can analytic semi-analytic subsets, then in costly dimension is integer. It's actually maximal local dimension. It could be union of point, graph, and surfaces. And if it's contained surface, it will be this 2. Yeah, but yeah, again, if it's your fractal set, it's sufficiently regular, the space type is a Hausdorff dimension, and if it's very regular, also for sufficiently regular fractals and both symmetric subsets, if you consider volume, it will be some constant uniform amount from below from above multiplied by this exponential growth which we see here. We get so we see epsilon per dimension in the isoperical volume, which is completely parallel to this thing here. Yeah, so really subtle that we get the parallel definition of dimension in completely different setups. Yeah, again, if you look at this geometric situation, when we define this Minkowski dimension, then it's maximum of local dimensions. If you get some part of your thing is 1 dimension, another part is 2 dimensions, so 2 will dominate. Yeah, so you should forget about 1 dimension part. Yeah, so it should be some notion of a local dimension, and for this exponential, the one can try to get definition of this local dimension at some point of critical locus. And the initial conjecture is that if you get a point in critical locus and consider sufficiently small neighborhood of this point, sufficiently small, then for any density supported on this neighborhood and strictly positive this point, the growth of the integral will be the same, it gives the same exponent, and that will be local dimension of this point. And then take maximum local dimensions, you get a local one. Yeah. Yeah, again, this, yeah, so we don't have to call it local integral, this really locally the point. And this local dimension is 0 when exactly we have more critical points and equal to total dimension when the function is constantly 0. Yes, and then it's subsequently. Yeah, so it's and if it has a definition, you should calculate integrals. Yeah, how good. So just to propose some formulas for the dimensions. You have got to how to summarize it. Just let's remind you a few things about vanishing cycles. Yeah, so I think that we have algebraic variety and regular functions. Map of fine line is map of algebraic varieties. And again, I assume that my critical locus is compact. It's a running assumption. Critical locus is compact. Critical value is 0. So on the 0 level set, we get something called shift of vanishing cycles. We can derive category of constructible shifts, and it has homology. And homology can be described as like global homology. Relative homology, global neural fiber, in the sense what you do, you take sufficiently nice open neighborhood of the full critical locus, and take pullback relative homology with respect to the fiber, very close to zero, and which will be this homological species in seconds. Yeah, so it's kind of topological description, but algebraic geometry through resolution of singularity and so on gives you a way to assert a mixed construct on this. Yeah, in this definition, we don't have algebraic parity because we get this open neighborhood, but also there are some spectral sequences and all the use of algebraic varieties. But it's kind of global notion, and this local notion of any point, local Milnor fiber that we got in the previous lecture. So you take just one point, critical locus, and what will be homological on the top of this complex of shift. You take again now a round ball around this point, and that's again homological pair. It's round ball relative to local Milnor fiber. And here you get new construction, even if this variety is not algebraic. For this local journal, because all together based on some resolution of polarities, and one can find mixed construction in this situation as well. Yeah, so get mixed construction, local, global, and but also get not one mixed construction, get variation of mixed construction, because again we scale the function. Just divide by running constant and C star, and we get variation of mixed structures on C star. And indexed by homological degree. Okay. And the definition is it's following the Stingray, who gave kind of an alternative approach to this spectra or complex index of singularity, so zero code structures. He defined what can make this following general finish. Suppose that variation of mixed structures on the star, the kind of algebraic geometry is quasi-important monogram. So we can define what's this fractional chord spectrum. It will be rational numbers with some multiplicities. Rational numbers provide this fractional part alpha from 0 and 1, including 0, and some integer part p. And when this number appears in the chord spectrum, if you consider direct sum of the rational structure, which is a generalized eigenspace for the monogram with eigenvalue exponent 2 pi alpha, is equal to 1. You get a variation of such structures not defined over integers anymore, but over 0.2. And consider which terms in Hodge filtration it has jumps from values of greater than 0. So it gets a p and get integer parts from Hodge filtration alpha from 1. And we get that together gets working now. And the conjecture is again looking for examples that the local dimension which we expect is converted from integrals, which I don't want to really calculate, is the maximum of this some combination of the things which you see from chord structure on homological local Milnor fiber or vanishing seconds. Take n plus 2 times this a plus p minus j that is homological degree, and take maximum of all these numbers. Yeah, so it's a way to kind of do practical calculation in with homology. In general, you shouldn't expect that homology, if you calculate homology in a similar way for global homology vanishing cycles, gives the right answer. It's very easy to hook up singularities of functions and many variables, so the global homology vanishing cycles is 0. The simplest way to do it is you, for example, imagine that you have more singularity. Your singular locus is, let's say, some elliptic curve, and contrast direction is sum of squares. But it's not canonical sum of squares, so consider out that monodromic minus 1, then get homologous coefficients in trivial system that vanishing things. Yeah, so these global things are local cohomology are always present, but global cohomology could be 0. And this is a situation which is relative to mirror symmetry, then the global cohomology are always on 0, when your variety has a holomorphic volume element. And this holomorphic volume element gives you non-trivial, always non-trivial plus in this cohomologous coefficients of finite cycles. And it seems to lie in place on the right. So it will be just in the middle degree cohomology, and it seems to lie in the can certify that you get a non-trivial piece of homology with appropriate numerical parameters, and this will be considered as a global dimension. So we have global volume element, then homological element which will be considered as intervals, which actually can be justified in other ways. In the definition of this number, I use some real density, yeah, with complex support, but let's ignore this notion of complex support. If you have holomorphic element, get square norm, get God given real density, which should fit to comparison between this homological and analytic pictures. Yeah, so for dimensions, one can understand, one can make approach to dimensions without mentioning this very tricky Hodge theory on vanishing cycles. It's kind of hidden in a certain way, namely, what you do, if you have variety as a function, you can consider the following sheaf. On variety, you consider sheaf of homological series in one variable u, or it's the same as epsilon, which we did before, and this differential ud plus multiplication by df. So you get complex sheaf with differentials, and you can make Delvaux resolutions. So you consider global d bar forms, and this consider the differential d bar plus d plus df. The Delvaux resolution way to calculate this complex homology. And if y is scalar in the neighborhood of original locus, then it's a free finite rank module over homological series. And here is a natural meromorphic connection, which has second order form. Let's explain the order of this connection in kind of basic example. I don't want to translate this convince yourself that it exists. Namely, imagine y is algebraic and f is a proper map. It's a kind of very nice class of Landau models. Then this hyperhomology integration can be linked to non-formal versions. So the formal family of homology consider an algebraic family of a fine line. You replace homology series by polynomials and now calculate homology in Zariski topology. And then homology you get wrong constants. If you calculate Zariski topology, you can show that it will get isomorphism, and now we get actual family of homology groups. And for u non-equal to 0, you can just rescale by differential by u, or you apply isomorphism on forms multiplied by u to the power degree of forms. So you divide differential by u, and now we take differential is coefficients and exponent of f over u. And the lattice space by removing Hilbert's exponents for irregular singularities simplifies the homology of pair. You consider your variety and points when it's range of some very large multiples of minus large multiple of u. Yeah. So we get actually each of the homology we have an actual Gauss-Manning connection. So this will be natural connection. Yeah. So it's only one way to see connection. Yes, it's also you have. And so now let's go to the general situation. I assume that my function has only one critical value 0. And then if we think about it, it implies that this connection has regular singularity at 0. a priori should have some singularity response, some critical values divided by u, but critical values as u. So it has irregular singularities. So what does mean regular singularities? It means connection after some formal normalization information, it became connection with self for the whole. And so what goes on? Now we define the vector space H, kind of global H, replacing form series by Lorentz series. It's a finite dimensional vector space operated by multiple degree over non-Archimedean field, series and non-variable. And what we have, I claim that this vector space on non-Archimedean field has two norms. In non-Archimedean sense, or valuations, because in non-Archimedean sense, case valuations are the same, and the first norm comes from the fact that its H is comes from vector bundle on non-punctured disk. So it means that if we get a section, we get order of loss of a section, we get natural variation. And conversely, this valuation with integer values, integer values gives you extension of the vector bundle to zero. Yeah. But I claim that we get regular singularities also gives you evaluation. Namely, because regular singularity, you can leave to see things called algebraic bundles over C star. This connection with regular singularity is from 0 to infinity. And now let's restrict these things to the array, positive numbers, and in the array get some flat sections. And then consider regular section sets of geometry. It's a linear combination of flat section with coefficient and some series. It will be roughly use a series, except maybe you get maybe not only a rational parameter but some shifts of some complex powers plus integer numbers and some polynomials and logarithms. And that for such object we have objects not what is order of growth when u equal to 0, and then we get some variation, but by real parts of this numbers. And in quite an important case, you get rational numbers. Now, so we get automatically, just the pure sort, we get two relations, two norms. And if you have two norms on a finite dimensional space, like in complex numbers, one can speak about singular values. Or not, in case you consider logarithm of singular values, you can simultaneously diagonalize two norms. And then it's different by some diagonal metrics, that's the log of norms of metrics of this vertical. Instead, a bunch of real numbers for comparison of two norms. And yeah, so that's things come from connections, it seems to give the same numbers which come from tricky Hodge theory, but it's with this connection only. And again, if you have volume element, then the maximal term of the spectrum should give the global dimension. Because this volume element should kind of like certify that some term of equation is not zero to the lowest term of equation. Okay, yeah, so that's different things, but it's bit formal, and I propose still another important dimension without center integrals, without Hodge theory, but in using some version of viewpoints, very old idea about the round complex, and it's applicable to real functions. Yeah, so remind me a little bit about this Morse Witten complex. So it was a long time ago, I think it's 84. Witten classical most important, it's using what we call supersymmetric quantum mechanics. Let's make this very trivial. Let's explain what is it. You start first with a compact Riemannian manifold and some real Morse function. So we forget for a moment complex manifolds and homological functions. Yeah, so now epsilon will be a positive number, not a complex number. And then what you do, you conjugate the round differential of force by multiplication by exponent of your function divided by epsilon. Epsilon is no positive number. Then you get differential will be when you conjugate, you get again ground differential plus multiplication by the g over epsilon, which is reminds me of what I've used in complex case, also multiplied by differential function divided by small parameter. Yeah, that was complex, now it's real. Yeah, so that this is conjugation, and I get twisted ground complex. This is differential. It's sorry? Yeah, exception, yeah. It's exception, yeah. Yeah, so that is twisted ground complex. Its commodity are the same as usual ground commodity. Because what we've done, we just nothing, we identify one complex ground complex with another multiplication that's smaller. Yeah, so it's as well as given by simplification, but it's not yeah, so it's split, yeah. Okay. Yeah, so it's homological are canonically identified with ground homology. And with ground homology. But now if you get any complex of maybe infinite dimensional space with reasonable functional analysis, you can calculate homology, identify homology with harmonic forms, which is kind of L2 minimal representative homology classes. So what does it mean? You have complex and you choose, because ground remaining has some norm everywhere. And now take, you have your differential of the epsilon, take Hermitian conjugate. Actually, it's totally real, you don't go to Hermitian, just and take common kernel of the six will be harmonic representatives. And the common kernel of differential and conjugate is a kernel of Laplace separation. Multiply differential based conjugate plus conjugate times itself, get some non-negative operator whose kernels intercept of kernels. And what is the observation of Newton? Is that when epsilon is very small, then eigenvalues of this new Laplacian, there are two types. The eigenvalues which were very, very close to zero became close and close to zero, and epsilon goes to zero. The eigenvalues is close to plus infinity. And there's nothing in between. So we large and large spectral gap between eigenvalues. So you can clearly separate the space in small eigenvalues and large eigenvalues. And moreover, some space explained by small eigenvalues, its dimensions finite and stays the same when epsilon is very, very small, and actually equal to the number of critical points. How one can see? So the story that is claimed that for each more single point, one can construct an approximate eigenfunction, not exactly eigenfunction, which is essentially concentrated in a very, very small network of this point. Yeah, one can do kind of model calculation in flat space. You have more singularity of index k, you get k negative squares and this positive. Then the corresponding form is harmonic form. If you write the equation, it looks like this. It's a very, very fast decaying Gaussian. It's one minus sum of all squares multiplied by x1 xk. And if you immediately can check if you multiply back to this exponent to identify this usual form, you get a really close form. Okay, so it will be this approximate eigenforms concentrated near most critical points. Now, how one can prove Morse inequality? Yeah, for example, it proves that total dimension of homology is less than equals the number of Morse points. Without doing cell decomposition, anything like this, what you do, you see that total rank of homology is multiplicity of zero eigenvalue with this Laplace. Homology, and zero eigenvalues is part of all small eigenvalues. So it's less than equals than the dimension of a surface of small eigenvalues, which is number of critical points. Okay, so people were very excited in the same 84 exploitation generalization. But I think that everybody misses kind of obvious generalization, which I want to introduce Next slide. One can ask the following question: what happens if singularities are not morphs? And in fact, what I want to formulate is something that will need very, very little from a manifold. I don't assume that now manifold is compact. And what I want to have a function, maybe with no more singularities, with degenerate and on some dimensional locus of critical points. What I need is that critical locus is compact. And in principle, one can imagine a certain situation like function like this, yeah. I don't know, something exponent minus 1 over x times something like that. You can imagine really pathological functions with infinitely many critical values, and I don't want to consider them just like single functions, just avoid some pathologies. Yeah, so I have this critical locus, and now I want to consider the following situation. So my critical locus, it's something on critical locus. I am getting some domain U1 and domain U1 and better domain U2, and all sits in my big manifold. What I want is this domain to have smooth boundaries and close to the compact manifolds as boundaries. Yeah, so you just nest between two domains, and now it has a definition that I think it works. What I do, I consider a space of forms in domain. Oh, sorry, in U2. Sorry, mistake. I take domain U2 and consider space of forms and integrate into those square of my form, into normal form, and just did the differential with my form, depending on some parameters. Again, bigger domain, small domain, we get one pre-filtered norm on the same space, one is less than another. When I make a completion, I get obviously contracted method between the spaces. Get contracted space, and then it has singular values in any kind of space. Singular values are now between 0 and 1. Because contracted. And conjecture that it's for this contraction, singular values again gets something like spectral gap. Say as I go to very close to 1 or very close to 0 when epsilon is very small. And dimension of the space when I get very close to 1 is 5. And it's uniformly, and it will be what's called, I don't know what's the right name, only index homological of my manifold with function. Well, what does it mean? Is the following: we get a map from a manifold to R, and assume it has only finitely many critical values, and we get my critical locus, component of critical locus. I surround by some nice neighborhood, which is manifold with a corner, so the function behaves nicely on the boundary, and consider homological pair. This is how my homological fiber changes when I cross a critical value. In the case of more singularity, I just do handle its generalization with handle, which I do all homological level. Okay. So how to identify this yeah, so I get this space singular values which are close to 0. And what I expect is again will be for epsilon greater to 0, it will be analogs of this Gaussian's support of critical locus and very fast decaying outside. So these things we can identify this quantity index homological sense in the following way. Yeah, so again, it's all things local, there are critical locus, and I assume the critical value is 0. And the dual space of this homology can be represented by some explicit classes. You take forms on maybe on one of this neighborhood, so that the boundary, the form is close outside some part on the boundary, near the boundary. And now what you do, the most basic things is if your element on this small set is very close to be harmonic representative, so we deal by distant differentials, it means that the exponent should be closed form multiplied by another closed form. The set, this whole thing is not closed thing, but you ignore the boundary because this expression faster decay outside, and take this interval and it will be the period. This indication not very canonical, but it shouldn't change much from what I explained. Yeah, so what goes on? You make kind of harmonic representatives in because the space is very complex, and in particular the space of this commode, which doesn't depend on next to so we identify this finite dimensional subspace in forms, this some homological pair, but the space of forms has natural Hilbert norm. It will be some very close to distribution supported with critical locus. It has something to norm, and so we get family of norms on finite dimensional complex vector space. We get a family of norms which actually can be treated as norm over norm variety, and the conjecture is that this family of norms behave in a way which you should expect a family of norms, like you know, have ellipsoids and depending on parameter, and they will grow with different powers of parameters in a different direction, give you certain stretching factors. The stretching factors. So formally, the conjecture said that for any non-zero vector, you consider well, it should be a little bit more careful. It's essentially you consider also vectors which we should do not one vector, but family of vectors of length 1 which approach to some given direction. This norm should go like some power, and this power defines the integration by real numbers, and that will be different dimension. Definition of dimension eventually this relation. I see that it's pretty different definition from what I started with, because before I started with oscillating integrals, take exponent I, the quantum mechanics are quotient classical cases. Here it's more like in tropical regime. They get real powers, very big real powers, and presumably should give the same picture. And now what we defined here is, was for real valued function. It's not for complex valued function. And if we return to holomorphic situation, and we have again volume element is assumed, then this volume element should be treating your manifold as real manifold. We get the function and take the real part of your holomorphic function, which has the same critical locus. Then you reduce you get exactly the same dimensions. Yeah, and here we get some little bonus, which was completely unexpected from the very beginning. When we calculate this in this, suppose we have Taylor metric, and this function, then we get this using the form of function, we take the real part of the rotated function, divide by small parameter, take this particular Laplacian, but because of Taylor identity, it's not Laplacian associated to another family of differentials. Then we consider d-bar differential plus holomorphic differential in common complex vector bundles and forms given multiplication by df. Yeah, so what we see, we get topological interpretation, make homomorphic interpretation. We get complex and holomorphic vector bundles, put some Taylor form of the dimension forms, and rescale differential we have in the low resolution. We have d-bar plus rescale differential complex, take square of norm and get harmonic representatives. And again, by similar identification, we can identify canonically homologous original complex. So that family of norms on homology. It's a very basic question, and so I get that for any complex of homomorphic bundles, homology, you get canonical filtration by real numbers on R gamma. Yeah, I already made a lot of calculation for this critical locus. I know what is it. I tried several months ago to do next example. Suppose I get complex of holomorphic bundles like on C2, resolution of some shift with zero support, namely, you can see the modules C of x1, x2, and divide by deal something like for basis will write like 1, x1, x2 will be the basis. Yeah, it's slightly more complicated than this double point in one direction, which has dimension 1c. So you can go to the definition, make this equation about harmonic form, and write equation about differential equation, which is pretty complicated. I still am not was able to solve it. I wrote on symmetric as some equation of fifth order with many complicated syntax. That's homogeneous solutions invariant on the U2. We reduce to ODE, equation of ODE, but it's still the early. I don't know what the fractional dimension even was in this case, yeah. But it's a really absolutely dramatic story. If you think about it, it says that any finite dimensional commutative algebra has canonical Will filtration. What is it? And it should be gives this filtration coming from this oscillating integral for Milner ring, but it will be something else over here. And yeah, no, it's very exciting development. We have no idea what is it. Yeah, and finally, I just want to say a few words about dimensions defined to be categorical languages. Yeah, so you have one element, sorry, from Y. There are two infinity categories. When you get, yeah, sorry, it's last chapter, more experience. Yeah, so this variety is homomorphic function volume element nature appears near simply as mere rules to find. And you have kind of two of this category, A model and B model in this logarithmic setting. The process will need this volume element. The A model is Okaizadel category, which is Z-graded category called the smooth proper, with invertible subfunctor. And then, again, according to all examples which you know from university, the dimension which I want to associate with things, it's naturally things which come from category theory. You consider X group between identity factor and very large power of third factor. Large positive power, large negative powers, that homology will be concentrated in certain interval. You divide by number of times you compose. Oh, sorry. Compose your. Oh, sorry, it's X subfunctor part capital N. Yeah, compose subfunctor N times and see where it implies and take motion to get some number. Why it's natural dimension? If you consider category of derived coherent sheet on some variety, it will be exactly dimensional variety because circumference it's line shift by line, increased by line bundle and shift by dimension. And very often this category responds not the whole category of coherent sheet, but some kind of terms of similar problem decomposition, which are fractional categories. So third factor raised to some integer power will be shift by integer number, and this fraction will be this fractional Calabi dimension. Yeah, and then if you have another category which is not C graded but C more graded, but it's Calabi category. And namely it will be a category of singularities. And how to sort number to this category? The idea is the following: you have this category of singularities. It has negative cyclic homology, which is this. So for example, this is a vector bundle of formal disks, and it carries that connection with a regular singularity. And I discussed for general story, you get connection with regular singularity, with normal connection, you get some natural spectrum and notional dimension. So it will be another origin. But it's in this case, if you translate back to what is connection, it's exactly this bundle of connection which is explained before. Yeah, so there are two particular things. And now, just for the conclusion, what dimensions we see from all real life examples, we get things coming from Deakin diagrams, the approach 1. This number is 1 minus 2 over integer. Then we can start other numbers, the simplest things which you big than 1, get 22 or 21. Yeah, so get some certain bunch of numbers. Yeah, so one sort should be minimal number, and also this fractional dimension of category of representation in A2, and norm forms the notion of exact triangle based on triangulation is the triangles in tree, it's the same tree which is denominator here. And yes, so one sort is on the notion of exact triangles to remember things, that it looks possible that this dimension from a well-ordered subset. So there's no infinite decreasing chain, which is a bit similar to what people expect for volumes of three-dimensional hyperbolic manifolds. Yeah, I think it's kind of more or less similar to yeah. Yeah, so it's bigger set of numbers between after the 0, 1, 2, 3, which we should kind of learn a lot.
Thanks for the talk. Any questions or comments?
With one more interpretation, maybe that's asymptotics and solutions and stuff.
But it's exactly what's known for the equation. It is just the same story.
Okay, any other question or comment?
Sorry?
I don't know, then the key of they are rational numbers.
Yes.
The perfect A2 is all what about all
Orbitals?
Yeah. Which orbitals are the
No. I don't think you can distinguish especially the orbitals from orbitals.
Well, we was here for them. I can't go check the card with the color. So there was like
Yes. No, so this, for example, this was paper by Polar and Demain for correct threshold. It's you have a lot of general singularity function, and you ask when one over absolute value of f bar s is convergent or not. For example, it's a homogeneous polynomial in many variables. If degree of polynomial is bigger than number of variables, it's adequate normal. If it's small, it's wrong. Yeah, that's what the thing is. They claim that they remove that like simple continuity by reduction, and they didn't. Yeah, you say we have to do something like maximum one.
Any other questions or comments? You can ask the case, so let's take this before the end.